All right, so everybody's is up and running. We're able to get some sort of analysis, right? I'm going to hit run, and there's my funky model. And yes, I get a model, and if you are using a Windows machine, you may or may not get a model. Don't worry about it because you don't need it anyway, and it's ugly. Okay, so we scroll down here, and the first thing that we run into is number of observations. Everybody have 1,029 observations in your data set? Perfect. Only one group. Number of dependent variables was just one. Number of independent variables is two. And here are our two variables. We'll also get a little bit of summary information on our variables that are included. We see that the average level of negative affect is 1.956 in our data set, and it has a variance of 0.448. We're going to need to know the standard deviation. How do we figure out the standard deviation based on the variance?
Square root is black.
Yeah, square root. Yep. So, the average of CDTS, the mean is 0.000. Why is that? It's centered. I centered those variables beforehand. The variance of distress tolerance is 0.788. Can somebody real quick calculate our standard deviation for distress tolerance if our variance is 0.788? Jiggs is doing it in his head. I am going to just pull out a calculator. So it is 0.78. Oops, I need to turn it this way. And I need the square root of 0.78, which I get as 0.88. Is that right? Okay. So standard deviation of distress tolerance is 0.88. This says that our model estimation terminated normally. We need to have that statement. Sometimes we'll have this statement followed by an error or a warning statement. And when we get those error or warning statements, we'll address those as they come. But we want to make sure that it terminates normally. If it doesn't terminate normally, then there's going to be some issues as we scroll down here. Most likely, you won't get any type of fit statistics. Now, we have the likelihood for the null model, and then the correction factor, and then the H1 model. And notice that those are exactly the same. Anybody want to take a stab at why that is the case? This will happen every time that you have 0 degrees of freedom. We have 0 degrees of freedom here. That is called what type of model? Just identified, right? Or fully saturated. Yep, absolutely. And when you have a just identified model, so here we have some AIC, BIC, sample size adjusted, BIC. Right now, these aren't all that important. They will become important when we start doing models where we don't have fit statistics. Because if you want to be able to compare models, then you want to have these things. There's a very nice paper out there by Raftery in Sociological Methods that talks about differences in BAC in order to claim a statistically significant difference in model fit. It's actually really, really liberal in how that, like, I think a BAC, a difference of 10 in BIC, he claims is equivalent. I will give you guys another way to test those called the Clark's distribution free test for these models where we don't have fit statistics. RMSEA is nothing, TFI, TLI. Basically, this is just a straight regression analysis, right? We have two variables, distress tolerance and emotional instability or affect lability, predicting negative affect. We see here that our intercept of negative affect is 1.956. That should match perfectly to our mean level of negative affect. And why is that? Why does it match perfectly to our mean level of negative affect? This goes back to ARM 3. Where's my regression folks from ARM 3?
That's the
It is the intercept. So the intercept.
The value of the dependent variable and
When the predictors are held constant at their mean, right? The intercept is when the predictors are held constant at their mean. And in this case, the mean is 0, right? So everything is centered. That means our intercept should match perfectly the mean level of negative affect. And it does. It's fantastic. We're doing great. Residual variance of 0.309. That doesn't have a whole lot of meaning right now, right? And notice we don't have any type of R squared here, right? Let's go back here and let's look at this again. Let's add in stdyx and hit run. And some of you probably had stdyx in there before. We run it, and now we will get what?
R squared.
We will get R squared, and also we will get standardized slopes, right? So here are our standardized slopes, and here is our R squared of 0.311. Notice here's our standardized residual variance of 0.689. And if you add this and this together, you should get 1, right? Because R squared can range from 0 to 1, and that is the standardized amount of variance in any given variable. And so if you are accounting for 31.11 or 31.1% of the variance, that means you are unable to account for 68.9% of the variance, right? Makes sense. Perfect. Yeah.
I noticed that the confidence intervals for the regression coefficients.
Say that again.
The confidence intervals?
Oh, yeah. It does not give you confidence. Is that what you're saying? There aren't any? Yeah. Yeah, no, that's a good point. There are not any confidence intervals here. You can calculate those confidence intervals on your own, right? And how do you calculate those confidence intervals? We've got the standard error, so what are we going to do with that standard error? What? Almost, not quite. What do we do with that standard error? We have to do something else with it first. By? Anybody? What do you multiply your standard error by in order to get confidence intervals? I mean, it's sort of the p-value. It's not quite. Yes. And so what is your test statistic? Like if we're talking about a standardized test statistic, a z test, what is our value for z in order to say that something is statistically significant or not? 1.96, right? So you will multiply your standard error by 1.96. Yeah. So make sense? Yeah. So you can calculate those on your own. But anyway, you can see just right here, there is a test of, in Stata, by the way, or I mean M+, calculates everything using a z rather than t or an f or anything like that when it comes to coefficients. SPSS, yeah, uses t for coefficients. Stata uses z also. Regardless, what we see here is that in M+, the test statistic for this slope is pretty strong, right? Like that's a z-score of 9.127. That is a pretty robust z-score. When we need to have a z-score of 1.96 to call that slope statistically significant, right? So, all right. Next, we are going to test. What did we say that we wanted to test for here? The interaction. So let's add our interaction. We have to put it in use vars up here. Let's start with that. And
you have to delete it though, right? Like you could have it there, but not use it in your model.
aha, let's do that once. Let's see what happens. What's going to happen? Somebody tell me what's going to happen if I do this. Nobody wants to tell me? I'll just tell you, your model fit is going to look like garbage. It's going to calculate this variable, and the variable is clearly correlated with other variables in here, specifically these two. and it's going to say like, hey, this model, you're not accounting for this variable, and the model does not fit very good if you don't do that. So let's go down and have a look, see what it tells us. I'll be honest, that model fit is not all that bad. But it's just sitting out here by itself, right? Here's the variance of this variable. We can actually include something in our statements here for output. We can put mod all. I actually prefer to use mod 3.84. This is going to give us what are called modification indices. And modification indices are, is M+'s way of saying like, hey, this variable is strongly related to this other variable, and if you add this slope or this relationship, you'll see a change in your chi-square of this amount for 1 degree of freedom. And that is why I use 3.84, because at 1 degree of freedom, 3.84 is the threshold for a significant chi-square difference, right? Anybody know that? Now you do.
I got an error, like, it's not letting me run it.
If you just include that variable, what's the error say?
It's like doing something similar to like what happened before.
Read it to me.
The input setup produced some size warning errors causing it to report. Please refer to the output file.
Huh. I'll come and look in just a second. Did you, well, I'll come and look in just a second. So if we add output, we add modification indices, we hit save, we run it with that crazy variable out there. And sometimes, just FYI, sometimes there are differences in how these things are handled between how models are handled between Macs and PCs, unfortunately. In fact, I think last year when we did ARM, we found out that my Mac was actually giving slightly different standard errors than the PC was. Anyway, there's the R square. Here's our modification indices. It's saying like, hey, if you correlate affect lability with negative affect, then you will drop by 999, which is the most it will give you degrees of freedom. This, if you're going to add any types of additional parameters, you should have a good theoretical rationale for why. Sometimes we'll add parameters, and then or we'll run a model and we'll say like, the modification indices indicated that these 3 paths should be freed. Now, if we're doing like a multi-group analysis, then it makes sense to go and free those. Like, hey, by the way, M+ said that there are gender differences on this path, right? So we just freed those so that they could vary freely by men and women. Incidentally, that's also called moderation, right? That's an interaction. That's when the relationship between 2 variables varies as a function of some other third variable, in which case in multi-group it's the grouping variable. But anyway, real quick before we go any further, I'm going to take a look at yours, and then we will keep pushing through to get this analysis going.
Yeah, that's have it but not have to be model. You can't just define it and then not use it. You have to use everything.
Apparently, like, you put model fit tool trash. That's basically what he's showing us. So I think he's still yeah, he's still showing us the trash.
Because I think with the modification, that's when you see.
Yeah, I kept saying it wasn't fine.
And then also I changed the context.
Sorry.
Hit run, and we should be good to go. Everybody able to run there?
It worked.
Awesome. Okay. So I'm gonna throw this variable back into the model, or actually put it in the model now. Throw it in here, and hit save, and we hit run, and let's have a look and see what it looks like. We still have a just identified model, but now we see that we do have a statistically significant interaction between distress tolerance and emotional instability, right? And so what does that tell us? Anybody know? When we're looking at these slopes here, we have a statistically significant interaction between distress tolerance and emotional instability, predicting negative affect, right? And so, what does that tell us? What do we know?
The relationship between the predictor on the outcomes varies at different levels.
Yes, perfect. And if we just say right now that emotional instability, ALS, is our independent variable, and distress tolerance is our moderator variable, looking at our coefficients there, what does distress tolerance do to emotional instability? We're going to go through and we're going to calculate this out, but just out of curiosity, what is it telling us? Yeah, right. As distress tolerance increases, we see that there is an adjustment in affect lability, and it decreases the relationship between affect lability and negative affect, right? So higher distress tolerance reduces the magnitude of effective affect lability. So we calculated what's the next step in a moderation analysis? Yeah, we're going to calculate our simple slopes now, right? We've already gotten our standard deviation, and so now we're going to do something really simple. Here is our effect right here, 0.348. Somebody remember that? Everybody remember that, right? This is the relationship between affect lability and negative affect when distress tolerance is held constant at its mean, in which case, in this case, the mean is 0, right? So 0.348, if we come up here to distress tolerance and we set it to 1 standard deviation above its mean, how do we do that? What do we do to set it to 1 standard deviation above its mean?
Just add.
Subtract.
Why
Oh,
subtract?
Yeah,
Why subtract, Colleen? You're right. I mean,
Uh,
why do we subtract?
because you gotta shift it. I can't explain.
No, you're absolutely right. By subtracting, you're actually shifting the mean to be lower than where the actual mean is, right? And by adding, you're shifting the mean to be higher than where the actual mean is. And so you subtract minus 0.88, which shifts the mean and gives us the assumption that distress tolerance is now higher than where it really is, right? And 0.88 was our standard deviation. 0.324 was our slope of emotional instability before. When we hit run, that relationship should be what? Higher or lower? Why higher? I thought we just said that as distress tolerance goes up, the relationship between emotional stability and negative affect goes down. Who says higher? Who says lower? Who says I am not about to raise my hand? Everybody. Okay, it should be lower. So we had 0.3284 before. Let's hit run. And let's see if it's lower. We don't have fit indices, so we're not going to worry about that. 0.228, that is lower than 0.3284, right? We increased distress tolerance which reduced or attenuated the relationship between affect lability and negative affect. In practical terms, this is real data with real people. What we're saying is that the relationship between, all things being equal, the relationship between distress or between affect lability and negative affect is 0.324. However, for those people who have higher levels of distress tolerance, for those people whose distress tolerance is 1 standard deviation higher than the average, the relationship between affect lability and negative affect is less. It's 0.22. Yeah.
I don't know. I'm still confused as to why we're subtracting 0.88 when we're looking at it one
Yeah.
standard deviation above.
Yeah, so what you're doing is you're subtracting a standard deviation from the mean, right? So if your mean is, if your true mean is 0, right? And you subtract 0.88 from everyone, right? You've just made your new mean minus 0.88. And you've set your true mean now. Your true mean is actually 0.88 above where you've just set that, right? So what you're saying is the true mean, which is where everybody's actually at, is much higher than the mean that you've just set. Does that make sense? You're shifting all of your data away from the mean below so that the true mean is now higher than where it actually should be, right? And vice versa. If you add, you wind up shifting all of your data up, and your true mean is actually much lower than where you've actually shifted your data to. So, does that make sense?
Kind of.
It makes more sense if you play with your data a
Yeah.
little bit.
I think
right?
it will make sense
Yeah.
over time.
Every 5 seconds, I understand it and then lose it.
You forget.
I mean,
No.
the important piece to remember is that it's just, no matter how many times you learn it or no matter how many times I explain it, it always seems counterintuitive. It seems counterintuitive as I sit here and tell it to you, despite the fact that I've been doing this for a decade and know that this is how it's supposed to be, right? So sometimes the best approach is just to say, okay, and move on. All right. So anyway, this relationship is now diminished. Let's go back and let's add. And by adding, we are doing what? Setting it to 1 standard deviation below. Yep. And it was 0.324, and now it is 0.468. And so this is saying for people who have low levels of distress tolerance, affect lability leads to even more negative affect, right? Like the relationship between affect lability and negative affect is much stronger if you don't have any distress tolerance.
Somehow have different numbers. Like
Oh, damn it. Yeah. What numbers do you have?
I have like 0.306 for CVS.
Wait, you have 0.306?
Minus 0.2.
I think that's the standardized model. Because I have the same thing. I have a model.
Oh, are you looking down here?
Yeah. Okay.
Yeah.
Oh, okay. Oh.
Yep, scroll up to the regular model.
I got it.
So here's the interesting thing, right? This slope and this slope should never change, right? Across all 3 of the analyses that we do, this interaction and this one, so we should have minus 0.23, minus 136. Let's look just real quick. Let's remove this. Minus 0.23, minus, what the hell were they? Gosh. Those seem like they were what they are supposed to be, right? The only slope that's going to change when you add the plus or minus standard deviation is the main effect slope, right? The interaction slope should not change, and the moderator slope should not change. It's just that main effect slope. And incidentally, r squared should not change, right? 0.329. I'm going to feel foolish if it changes here, and I just said it wouldn't, but let's run this. 0.329. All right. So now we have probed this simple slope, and we have shown that we have found the association between affect lability and negative affect at mean, high, and low levels of distress tolerance. We've got a way to describe that. What's our next step?
Plot.
Plotting it, right? And so how do we plot it?
Excel.
Excel. So I have given you guys a fancy little Excel sheet to plot them on. Did somebody in here email? No, it was somebody from a previous ARM class who had a three-way interaction, and he emailed me over the summer, and he's like, hey, how do I make the same thing?
Was it Michael?
It was Michael. Michael said, I've got the two-way one. How do I do a three-way one? And to which, did he tell you what I told him?
No, I never got the answer.
I said, I taught you how to do this. Do it and send it back to me. And he did, and he figured it out. I mean, yeah, it was fantastic. He did a great job. I was so happy, right? Like when people are able to take like what you learn in class and then extend that a level, it's as an instructor so reinforcing. It was Michael, and he was able to do it, and it looked awesome. Okay, so I put there's an Excel file on your guys's thing there, whatever it's called. What is this called? Web courses. So pull up your Excel file or download the Excel file. Let me see if I can find it in my garbage here. I might just have to download it because I don't know if I have.
It's called linear_2.
Yeah. Or you can just click on simple slopes right there. Oh no, I gave you guys the wrong one. Oh wait, maybe I didn't. Maybe I didn't. Oh, sheet one, there we go. Nope, I did not give you the wrong one. Perfect. So this one that I gave you here, though, only has high and low. It doesn't have mean. So let's step through this. First of all, we have a graph over here. Has everybody grabbed this? Okay. So we have a graph over here, right? And then we have the x slope, the z slope, the z times x slope, the intercept, and we have standard deviations. We have this, which is our x-axis, right? That is these values right here. And these are the values for our y-axis. This is something that I did when I was a graduate student, because graduate students sometimes do crazy, ridiculous stuff that wastes time. So we have, I think this is actually this is really valuable to do this though, so we'll do it here in class. What is our x slope? We're going to pull this from our m plus output, and the slope of x was what? Say that again. Point.
It was like 0.3 something.
Yep. Point 3. What was it? 0.348. Now we want to get this when everything is centered. So let's run this again. .348. Perfect. So let's plug it in. 0.348. Enter. What was our z slope? Z is our moderator variable. Minus point what? Say that again. 232. Is that what everybody else has? 232, and then our interaction is, yep, view. How's that? Perfect. What is our interaction? Somebody read that to me. 136, and our intercept I think was like 1.922. Is that right? All right. If we come over here, it says positive frame, negative frame. We're just going to call this low, well, we'll call it -1 SD, and let's go +1 SD. Oh, and we should probably put in our actual SDs here. What is +1 SD? 0.88, and -1 SD was -0.88, right? We come over here and we look at our slopes, and we can see that it looks kind of wonky, right? So the issue right now is an issue of range. We don't know what the range is. We've got this range of x that goes all the way to 100, and this actually gets adjusted based on what this stuff is, but I don't think that our x actually goes to 100. What is the range of x? How do we figure that out? Yeah, we can do descriptives, or we can come over here and we can look at our x variable, which was what?
Is the X CLAS or CDTS?
It's CALS.
Okay, I keep getting.
CLAS is like an anxiety scale, right?
It's affect lability. It's how much your emotions go up and down. Yeah. So I call it emotional instability, but it's called the affect lability scale. But yeah, it's like how much, and I just love this little scale, and I love this measure because my very first paper was using affect lability and showing that, like, this is a complete aside, but you guys, I do substance use research, and one of the things that really fascinates me is people that are able to smoke and never get addicted to cigarettes, right, to nicotine. There's this group of people called chippers that, like, they can smoke a few times a day. They can, yeah.
I'm sorry, I keep like interrupting you randomly.
No, that's okay.
So I don't get the descriptives for some reason.
You don't have univariate sample statistics? You don't have it either. Oh, that's interesting. You have version 7? Oh, yeah. So if you're using an older version of M+, this is a newer feature that M+ has. It didn't have it in version 7. It came out in version 8. Yeah. So if this happens and you are not able to get them, make sure that you email me and say, like, hey, can you also give me the SPSS data set for this, and I will make sure and provide
So there's no
those.
command just to a hospital?
There isn't, not in 7. No, unfortunately not. Anyway, what we can see here is it gives us our minimum and our maximum values for affect lability, and our minimum value is pretty close to -1, and our maximum value is pretty close to 2, right? So if we flip back over here, we are going from 0 to 100. Obviously, that's going to be well outside the range. Let's change this to -1, and let's go 0.25, and then let's just grab this and pull it down a little bit here. Pull it all the way down. I'm just going to delete these. All right, so what happened?
Actually, you just said again, sorry.
Yeah, I'll show you what I did in kind of slow motion here. I set this top value as the lowest possible range, which was -1. Then I said, I have a command in here that says, like, hey, this value should be the value right above it, D4, plus 0.25. And then after I set that, if you just grab it and drag it down, then it will do that for everyone. Then the next one will be D5, D6, D7, and so on. Say that again?
My graph is wavy. It's like
It's wavy?
Yeah.
It's very interesting. I see it.
All right, let's have a look. Colleen.
I mean, I guess it was bizarre.
So stop it. I will just. So for right now. There you go. All right. So your graph should look something like this right now. We know that this actually goes to 2, so let's hop in here. Number, scroll down. Oh, not number. Is it tick marks? No. Oh, at category, at maximum. Why is this? Oh. That is not what we want. Oh, here we go. So automatically select based on data. We don't actually want that. We want it to go from -1 to frustrating. Okay, somebody's gonna have to help me out here because my graph just crashed. Oh, it might actually open it back up to where it was. Probably not. Nope, that doesn't look right. Okay, real quick, somebody tell me the x slope. 0.348. Z slope minus 0.232 minus 0.136, 1.922. 0.88 minus 0.88 minus 1 0.25. Don't do it again. Okay. Grab that one, pull it down. And then we can actually just rather than try and extend it there, if you click on the slope and you want to extend this out further rather than going and monkeying with it, you can just click on that and then just say like, hey, we're gonna go to 2 here. Same with this one, let's go to 2. And it will extend it out to 2. I'm gonna save this on my desktop real quick. Just so that if it crashes, I don't have to go back and redo this again. This one, we will have to adjust, and so we can adjust it. We've got a minimum of 1. Let's do a maximum of 4, because I believe that negative affect ranges from 1 to 4 in this data set. All right, so you should have a graph that looks something like this. Negative affect. This one down here is mean-centered what? Affect lability. We're going to call this low DTS, high DTS. All right, so we have this cool graph, right? Was everybody able to follow what I did there? Whose graph does not look like this? Let's have a look. Oh yeah, so just click on this. Just click on the, not double click, but that's probably just grab this and drag it down to do the same thing with that. Same thing with the next one. Perfect. Then click on here. Double click. Oh, yeah, this one. And minimum should be 1, maximum be 2. Perfect. You can relabel stuff later. We're not going to worry about that right now. But so we have this. We have these two slopes, high levels and low levels. This is when distress tolerance is low, right? This is when distress tolerance is high. And we know the slopes of those, right? This one was like 0.48 and this one was like 0.22 or something, right? What are we missing here? We're missing something. Mean values, right? How do we figure out mean values? We have, yeah, David, go ahead.
Instead of using the one standard deviation above it, now we just use 0.
Yeah, we just use 0. So we can do this, right? We've got this equation that I've already typed up in here for you guys. We can grab it, drag it over. So we have this new equation here. And then we have to modify our equation. So we have E3. What is E3? That's the effective x, right? We need to keep that, plus E9 times G3. What is E9? Our interaction. And what is G3? Oh, so we need to get rid of G3. Let's just call it 0. Times D4. What is D4? Yep, and that one, we need to keep D4, so we won't change that. Then we have E12. What's E12? That's our intercept. Plus E6. What is E6? Z-slope times G3. We know that G3 is our 0, right? We gotta make that 0 again. We hit enter. And then we can grab this and just drag it down. And you can do just kind of a quick check here. Every one of these values should be in between this value and this value, right? And they are all the way down to the bottom. This is higher, this is lower, that's right in the middle. How do we get it into our graph over here? Yep, before we do that, real quick, why did I just substitute 0 in here again? Yeah, right. This is actually assuming a high value for our moderator. This is assuming a low value for our moderator. This, we want to assume the mean value for our moderator. And with centered variables, our mean value for our moderator is 0, right? Yeah. Okay, so if we want to add our new slope over here, we click in here. And then you right click or left click or whatever. I'm a Mac person, so I 2-finger click. I don't even know what PC folks do. And we're going to go select data, right? And once you're at select data, we're going to say, hey, we're going to add something here. We're going to name it whatever this is up here. We haven't named it yet, so we'll come back to that. And the values for this, whoops, should be right here, right on down. We're just going to go to 2 because that's where that one goes, right? Everybody following so far? We all tracking? And when I hit enter, what's going to happen? Crazy little line should pop in here, and it does. Let's name this now because we clicked in here and said that we're going to name this. So we're going to call it mean DTS. And it pops in there just like it's supposed to. And my OCD is flaring up looking at this green line. So we're going to click in here. We are going to do just a solid line. I don't like that color. I'm going to use black. And I will use something like this. Oh, shoot. And then you know what I did? I just clicked the line segment rather than the entire line. Click out of there. Click on the entire line. And now... come on. There we go. Okay. Now I can do everything that I want. Solid line, black, and there. Perfect. Okay. Everybody have a figure that looks something like this? Yeah? There's one other thing, and this is just my personal preference. I hate that mean. I like it to be in between there, right? Like, why would you have low, high, and mean? That makes no sense to me. So you can adjust that by going select data and just taking mean and moving it up like that. So you just click the little arrows there, hit OK, flops it around. There we go. And that is a nice, reasonable figure for a paper, right?
Do you need to have all three, or is it fine?
You don't need to. I think I know that when I review manuscripts, I hate it when people here's my two pet peeves when it comes to simple slope figures. One is when they just have high and low and they don't have the mean in there. Granted, that mean is like less important. That high and low says that, hey, there's a fan of effects here between 1 standard deviation and -1 standard deviation. I just like to see it, right? Like all things being equal, here's the average effect. The other thing that I really, really hate more than anything is when the X is just like 1 standard deviation, 1 standard deviation. Oh, I can't stand it. Like, give me a range of your data. Show me what these slopes look like across that range. Don't just give me 1 standard deviation. It drives me crazy. Yeah.
For your x-axis, how did you get it that it only stops at 2?
Yeah. So you can click on a slope, just a single click, and then it'll highlight that slope, and you can change it to whatever. And so I just clicked on it and moved them all to 2.
Okay.
But you can do it that way.
Perfect. Thank you.
Yep. All right. Let's take a 10-minute break. When we come back, we are going to do mediation and moderated mediation.